Okay. Is that it? Try half degrees right. Okay. 3 degrees right. There is something there. Yep. Following it.
Welcome aboard our galactic safari in search of extraterrestrial life. This is a mission into deep space. The creatures we will encounter are based on the scientific understanding of the nature of evolution. Stand by for video briefing.
Never before has the screen reached such heights of excitement, breathtaking spectacle, hair-raising terror.
Love-hungry spacemen come to seize our women that their dying race may live.
The trouble is that when people invent aliens, they tend to give them a nose, a mouth, a face like ours, because otherwise people don't recognize them. They can't see the creature if they don't see a face.
Explode the bomb.
The human form is a shape that has evolved for us. It's unlikely to have evolved anywhere else in the universe on any sort of planet, even a totally Earth-type planet.
Surely now you will declare war upon the Earthmen.
Aliens have always had a very bad press in science fiction because they've always been used as figures of menace. There is a sense in which aliens are a reflection of our own anxieties about ourselves.
If you want a plausible alien, you have to think of an alien's environment, and you have to think of where it evolved, and you have to think of all the other creatures around it that evolved with it as well.
Perhaps a better example of what extraterrestrials could be like would be a Dalek, where it's a little bit different, where it doesn't have two eyes, it doesn't have legs, could quite easily come from a planet where the surface is very flat. No problems. It doesn't have to get over rocks and boulders and so on.
Now that we've got sophisticated, we want a real ecology, and we want something that works. No longer can we have a planet with oxygen and no life, or plants and no animals. We now have to have something that conforms to the geology that everybody knows, the astronomy that everybody knows, and we can't get away any longer with simple-minded biology.
Goading them to lure men into the den of bloodthirsty moon monsters.
What I'm interested in are the real aliens, the ones which, to me, sound credible. Many people think that because we have only one example of evolution, the evolution on Earth, that we can't argue from it what kinds of things we're going to find on other planets. But actually that's not true, because on Earth, during the history of life on Earth, some things have happened very many times. There are very many creatures that have invented flight. The insects, the birds, the bats, all fly. They all are very different flyers, and they don't all descend from one animal that invented flight. They all invented flight independently. Just as fur on the bumblebee and fur on the mouse to keep them both warm is another invention. If we ran evolution again on this planet, such things would happen again. We wouldn't get birds and we wouldn't get bats doing the flying, but we'd get other creatures doing the flying. We'd get other creatures with the fur. Another example, of course, is eyes. Lots of different creatures have developed eyes, and they've developed some really rather peculiar ones. Scallops have developed eyes all round the edge so that they can look out all round their shells. Insects, of course, have these wonderful, multifaceted eyes. Then, of course, the octopus has eyes which are remarkably like the eyes of vertebrates. They're like our eyes. They all invented eyes independently. That's why I call them universals. Universals are things that would happen every time you ran evolution on Earth. And of course, if you're running evolution on another aqueous planet that we find somewhere else in the galaxy, they will happen there as well. They'll happen to quite different creatures.
To see an amazing variety of possible life forms, we can travel back in time. Planet Earth, 530 million years ago.
One of the obvious places to look for aliens on Earth would clearly be to go back in time through the fossil record to some of the earliest animals in the sea. One is an enormous predator known as Anomalocaris. The front of this animal was equipped with a couple of large jointed appendages with an array of spines down the side, which it was able to use to capture its prey. And it pulled this prey up into a mouth which looked rather like the diaphragm on a camera, which was armed with rather fearsome looking teeth. The body itself was clearly elongate and tapered, and it swam with not just one pair of fins or even two, but with a whole series of fins that ran down each side toward the tail. A second example is provided by Opabinia. Opabinia is characterized by having 5 eyes on the top of its head, and it was also a predator, but instead of having these grasping limbs like those in Anomalocaris, it had a long proboscis-like structure, a bit like the trunk of an elephant. And the suggestion has been made that it swam around looking for worm burrows, and when it was time to dine, it inserted this proboscis, plunged it down into the holes, and grasped the worms and hauled them out. So in both cases, these would clearly be animals that are quite different to anything that we see today, and which have been categorized by some paleontologists as the weird wonders of the Cambrian Sea. So these are, if you like, from our perspective, aliens on Earth.
There was a great variety of creatures in that Cambrian Sea, and nearly all of them died out. They have no representatives today. Of course, we're the representative of one of those creatures, a little thing called Pikaia. But what would have happened if Pikaia had not left any descendants, if it had died out, and one of these other things, perhaps Opabinia, had been the ancestor of all the land creatures? Well, we'd be quite different. We'd have a damn great thing coming out the front, and we'd be talking to each other in a quite different way. We'd be aliens.
Return to the present day complete. We are now approaching Mars. Preparing to fly by the Martian surface, scanning for life signs.
Mars is a fascinating target because it has evidence that there was liquid water on its surface at one time. And liquid water is the most important missing ingredient. And here on Mars is the only other place that we have direct evidence that there was liquid water outside the Earth. It's not there now, but we know that it was there at one time, and that's what causes many of us to focus on Mars, early Mars, as the site for searching for evidence of past life. We're talking about a planet here that at one time we think was as complex as the Earth. It had active weather, it had water, it had rivers, it had lakes, it may even had a biology. That biology is probably as interesting and maybe different, and interesting because it's different than ours.
It's entirely possible that life could have arisen on Mars at the same time perhaps as life arose on the Earth. It could be that the best we can hope to find are fossilized Martians, these tiny little bacteria-like creatures that have been described by American scientists. However, it's also possible that life could have retreated into the rocks and is there in a sort of hibernating state. It's there as some type of spore. It's waiting for the conditions to arise when it can blossom again.
meteorite warning, altering course to avoid impact. The zone between Mars and Jupiter is strewn with debris, leftovers from the formation of the solar system.
We know that one way that life can get from A to B is for a meteorite to crash into a planetary body and send lumps of rock out faster than the escape velocity for the gravity of that planet. If a meteorite hits a polar region of a planet that has evolved microbes, then instead of being a lump of rock that would fly through space to another planet like the Earth, it'd be a lump of ice. It'd be conceivable that one of these big dirty snowballs fell onto the Earth, melted in our oceans, and released the microbes into them. So we may well have relatives from deep space, or we may have even come from deep space. Who knows?
When we look at the history of life on Earth, we find evidence for life at 3.9 billion years ago. The Earth hadn't even finished forming, and we see evidence for life. Well, that's kind of puzzling. It sort of belies the notion of life as being a slow cooking of a primordial soup from which the first cell oozes out. And it's given more weight to the notion that life is spread cosmically by comets.
We are now entering the gravitational pull of the largest planet in the solar system.
Jupiter is very nearly a star, and it's not really the same sort of planet as the Earth and Mars. It's not what we call a terrestrial type planet with a rock core and mountains and a solid surface. If you try and send a probe down there, it's going to gradually disappear into an ever increasingly thick atmosphere, into possibly a soup, or eventually into a liquid.
People have talked about life in clouds on Jupiter. Somehow life requires something more stable than a cloud. And I think the evidence of clouds on Earth are telling us that. So for that reason, I wouldn't really suppose that there was life in the clouds on Jupiter.
Approaching one of Jupiter's largest moons, Europa.
Europa is covered by an ice sheet. This ice sheet is broken up just like the polar ice sheets, like the pack ice in Antarctica. And it's now thought that there is liquid water underneath. And that is what is exciting for a biologist to speculate, if there's liquid water, could there be some sort of system evolving under there, which we could interpret in terms of life as we know it?
To me, the most likely place to find life today, alive now, is on Europa. If, as we get to Europa, we find that indeed it has an ocean, and the tantalizing new images from Galileo suggest that it does. If we take that as given, then there's an ocean on Europa. Can life originate in an ocean? Well, in fact, our current theories for the origin of life suggest that life originated at deep sea vents. So that would be very consistent with life originating at the bottom of an ocean on Europa as well.
There are places on the Earth where you might well have similar systems. These systems can be quite sophisticated. Not only do you get bacteria living around these black smokers and the very deep ocean layers, you also get worms, and really quite big worms, which can grow over a meter long in their growing season. So just because the environment seems hostile to us does not mean to say that you don't get some living systems developing in it.
Life around Earth's deep-sea vents can give us valuable clues to the possible evolution of life in the seas of Europa.
To make a kind of plausible guess, allowing what we know about physics, chemistry, and biology, about the kind of life that could be there, you must start off with the vents. That's obviously the source of energy. And I can imagine bacteria building a little wall, just like a little wall of bricks, and getting higher and higher. And then I think, might plausibly imagine, that it would build up a tube around the vent. Now, other creatures evolving from those bacteria, or some bacteria who are using another way of life, are going to browse on those. And you're going to get a whole ecology based on these vents and the creatures that live around them.
Commencing descent into the seas of Europa. We are looking at huge towers of bacteria, rising many miles above the ocean floor. Inside these vents, warm water rises, nourishing layer upon layer of bacteria. Feeding on these bacteria are schools of giant fish-like herbivores. Trunk-shaped mouths pierce the vent to suck in vast quantities of bacteria. These grazers are territorial and, like squid on Earth, flash warning glows to drive away rivals. Predators, streamlined for speed, prey upon the grazers. Europa survey complete. Retrieving data for journey into deep space. NASA's Hubble Space Telescope is searching our galaxy for new planets. Some astronomers speculate that there could be thousands of planets with the right conditions for life. Initiating warp drive and a journey to the outer limits of the imagination. Gravity survey. Throughout the galaxy, there are worlds of different sizes and varying gravities. The larger the planet, the higher the gravity. It's the key force in the universe. It's why planets are round. It even affects the evolution of life itself.
I can imagine a world of lower gravity where things would probably be quite different. Insects, for example, that have wing muscles so they can fly and against gravity and maintain a position in space, would probably learn to soar, because with lower gravity, they wouldn't be pulled back to Earth quite so fast. Animals that are used to running fast would probably learn to jump more and perhaps glide to where they were going, because with less gravity, it's also probably a little more difficult to stop quite so fast, because gravity helps you stop. You'd probably see differences even in animals in the sea who now have to maintain a neutral buoyancy, which is effective gravity also. And so it would be easier for them to swim to different levels than it is currently. So you might see changes in swim bladders or other organs associated with gravity effects. So I think that a planet with lower gravity would probably produce creatures quite different from what we're used to seeing on Earth.
Surveying the larger planet.
A high-gravity planet isn't high gravity all over. If you're in the sea, and that's where all life starts, there's very nearly no gravity because you're much the same density as the stuff around you. It's when the animals come out on land that they feel the gravity. Even on Earth, crabs have had to really compact themselves, and their limbs are much shorter and sturdier, because if they're going to lift that weight against gravity, they have a real problem. On our high-gravity planet, we would expect to find creatures that have more limbs to hold themselves up, are really finding quite a problem in getting around on land when they're free of the buoyancy of the water. But paradoxically, flight might be easier, because there might well be, in fact there should be, a much denser atmosphere. And that means that you don't need really, really big wings. I mean, don't think of flying elephants here. This is the reason, of course, why insects on Earth never got bigger than about this. When they came out on land, their ancestors had been in the sea and were buoyed up. When they came out on land, they couldn't shed their skins without collapsing. So you only get little insects on Earth, not the big ones that some science fiction films have portrayed. But on our fictitious heavy gravity planet, what we've decided is that there's a new way of dealing with this.
The pteropede may be able to take advantage of the denser air to fly, but high gravity can lead to a bumpy landing. To support its great weight, the creature's legs are directly under its body. It breathes through lungs in the tip of its tail, which is more efficient than the way insects take in air. So the pteropede is able to pump oxygen through its large, heavy body. To grow, the pteropede must enter the water. It is only in the buoyancy of water, where gravity has little effect, that the pteropede can shed its skin and increase in size. Once the new skin has hardened, the pteropede can return to the demanding heavy gravity environment on land. Other inhabitants of this planet have also evolved adaptations to cope with intense gravity. The Sputnik bug has spines to protect it from a dangerous fall. Sadly, the splatterbug has nothing to protect its soft body. It's an evolutionary dead end. We are now approaching a solar system with 2 suns. We can expect to find extraordinary seasons on the worlds which orbit around them.
The majority of stars in our galaxy, and indeed the universe at large, as we understand it, are actually binary stars, not single solo stars like the Sun. They're systems of 2 stars rotating about a common center of gravity. Of course, seasons develop simply because the orbits of planets around stars usually are not circular. So at certain times, the planet is further from its star and its source of heat than at others. Therefore, we have winter and summer for that reason. Now, if we have a 2-star system, then we have our Earth-type normal seasons operating for very long periods. But then, as the second star approaches the first, we're bringing a source of great heat and light closer, and we're going to have a very short, sharp, warm season, which is going to change everything, life, the pace perhaps of evolution, for a relatively short period, and then the star will disappear off into the vastnesses of the system, and the original conditions will return. You have the perfect stage for a story of conflict and change.
Visual contact with planet Heliconia, in orbit around a binary star. Location, the mind of Brian Aldiss.
What Heliconia is, it's one planet of 4. They orbit about a rather dim star called, to the inhabitants, it's called Basilix. But Basilix itself and its planets is on a long, slow orbit about a very large powerful new star, which they call Freya. I was determined that Heliconia should not be a mere fantasy. And in fact, I had astronomers to assist me.
The conditions that we imagined for Heliconia had to be believable, they had to be workable, because the main thrust of the story is the conflict between the humans, who could only survive really in the nice, warm summer period when the two stars were close by, and the Phagors, these primitive hairy beasts who were very resilient to the very unpleasant cold conditions. So the conditions had to be acceptable to both kinds of biological development. And that's true also, of course, of the trees that he dreamt up. They had to be able to survive these incredibly long winters, sort of hibernating, and then have the capacity, the biological capacity to blossom out and gain their sort of life substance from the very short summers.
We tend to think of seasons based on 1 year, but there are places on Earth where it doesn't rain for 10 years, like deserts in South America. And when it does rain, they become just a forest of beautiful flowers, which appear within a few days of the rain falling. You can also have microbes that live inside the rocks of Antarctica, which will take in 1 molecule of carbon dioxide and not release it again until 10,000 years later. So you can think of that as a growth period, a generation time of 10,000 years. So we do know about these things on Earth. So you have to be broad-minded about a concept of a season on a planet in another part of the solar system or elsewhere in space.
Continuing our search for life in the far reaches of the galaxy. Life signs detected in the dense atmosphere of the imaginary world, Sufuria.
Life could possibly also exist on planets that are totally unlike the Earth. For example, this one that I call Sufuria is a planet that geologically is very much like the Jupiter's moon Io. There are a great deal of sulfur in its makeup. And I've given it an atmosphere that's very much like Jupiter's atmosphere, very thick concentration of gases that would be, to us, totally noxious. There would probably be living things that would be actually anchored on the solid surface of the planet, but would gain their energy from the sunlight coming in at the tops of the clouds. And these creatures, I don't call them plants, I don't call them animals, but their structure would be very much like barrage balloons. Supported by gas which they have generated themselves, but still tethered to the ground by a massive great stalk, maybe thousands of kilometers long. In structure, these would be very much like the great kelp seaweed of the Pacific Ocean, where you've got the photosynthetic leaf up near the bright levels of the ocean, but it's still anchored to the darkness at the bottom of the sea. All living things, even these strange ones on this planet of Sufuria, still need to reproduce and grow. And in the case of these gas bag creatures, they reproduce by the individuals rubbing against one another, exchanging genetic material. The youngsters bud off from the parents, and they grow a long stalk down beneath the gas bag. And when that's long enough to touch the surface of the planet, then the youngster breaks off and becomes a totally independent individual. Here's a creature that migrates between the energy-rich levels at the top of the atmosphere and the food-rich levels at the bottom. As a youngster, it attaches itself to the gas bag of the balloon creatures and extracts oxygen from the gas inside the envelope. And having stocked up with oxygen, it then parachutes down through the murk of the atmosphere to the surface of the planet itself.
Shedding their parachutes, the young worms feast on the nutritious roots of the balloon plants. When they have fattened up, the adults begin their epic journey back up the stalks to mate. The parachute worm is a perpetual migrant. Its life cycle, a response to this extreme environment. Life signs detected on Epona, an imaginary but plausible world, engineered by a League of 35 scientists and writers. Called the Aona Project, their ecosystem is the most elaborate yet conceived.
Life on Epona began in the sea. One of the ancestors of life on land had originally 5 forelimbs and 5 rear limbs. As it developed into land ecological niches, each of the limbs became specialized in different ways. So now we have a large variety of very interesting and bizarre animals.
The founding principle was to design a world that fit within the known bounds of science.
The plant life on Epona is rather different from what we would find on this planet. The pagoda trees and other myophytic plants are capable of defending themselves to some extent. They can, if an herbivore would come to nibble on them, pull their branches out of the way. The reason for the circular leaf patterns on the pagoda trees is because they needed to maximize the surface area on the leaves to get as much carbon dioxide as possible.
One of the creatures that I had the opportunity to invent is called the spring croc. It is the major predator on Epona. It lays in wait for its prey, usually partially submerged. It's extremely vicious. It doesn't, it's actually a lot like the earth shark. All it really cares about is eating. It doesn't have to be intelligent. It just has to be quiet.
Uthers developed from a flying fish. They started off in their avian lifestyle hunting the salacopods, and then kind of graduated upwards to carcasses that they would find, and then started herding themselves because, you know, why wait for something to die when you can end up killing it yourself and, you know, you get dinner that much faster. Another thing I should mention is boost, which is a combination of hydrogen peroxide and ethanol, which hyperoxygenates their blood, and it allows them incredible stamina.
What the project has contributed is to show that you can develop a fantastic, incredible place and still make it believable. These are still based on the same laws of physics that we know, the same laws of chemistry that we know. We're not asking for someone to throw away Einsteinian theory to be able to believe in this place. So we feel that that is something different from what a lot of people have done.
We are now approaching Greenworld.
Greenworld is my idea of an Earth-type planet. Any life would be based on the same biochemical principles as the life on Earth. When I developed the animal life of Greenworld, the first thing I had to do was to go back in time and follow the evolutionary stages that will get to the present-day animal life. So if we go back 600 million years to when all animal life in Greenworld lived in the sea, all the animal life consisted of bottom-feeding animals, a bit like starfish. And these would have a radial symmetry. They'd be built a little bit like a wheel, with legs radiating out in a circle. Now, when the animal life evolved into land-living creatures, they developed what we call a bilateral symmetry, where you've got a line down the middle of the body, and everything is arranged either along that line or in pairs at each side. The curly whirl is an animal that lives in Greenworld trees. You can see its evolutionary origins in the six-armed starfish shape from which it evolved. If you could take a six-armed starfish and pull it out into a long, thin thing, this is the shape that you'll get. The sensory organs are still on the top, but they've largely moved forward as well, so it can sense where it's going. Now, the animal that I call the pud is an example of the animal that has developed a bilateral symmetry with two pairs of limbs and one leg at the front and one leg at the back. And it hops about on this massive great hind leg, which has grown very, very large to take the weight of the whole animal. Now, there are thousands and thousands of different species of these. They're very much like Earth's beetles in the range of shape and habitation, but they're all built along the same design. All these animals are very interesting in their own right, but they would actually live as part of an ecology. They would all interrelate with one another in one way or another, just like things do on Earth.
Reading Greenworld images. In the lush tropical forests on Greenworld's equator, a group of puds forage in the undergrowth. They scavenge on fallen fruit. But the puds have many enemies. The scent on the breeze alerts one of them to danger. The armored quank is the anteater of Greenworld. Interrupting transmission. Unidentified object approaching. Sensors indicate a crystalline structure, alive but with no organic content. Analysis, intelligent machine alien.
When we're looking at life forms, even on Earth, we tend to put human values and animal values and say, this is alive because it's like us, or this is not alive. When we go to another planet and look at what's there, what could be alive, we should be much broader in our outlook. It could be quite easily a machine life form. If it can communicate with us, if it can communicate with other machines on the planet, it could be a whole machine-based life form that we're looking at. So I think we've got to be much broader in how we view life. It's not just humans, machines can be alive too. So I think our first encounter with an extraterrestrial life form is almost certainly got to be a machine life form. If we look to a probe travelling through many, many galaxies or solar systems, quite easily, once it's out of our solar system, could just switch off, just switch down. Move through space. When it gets into a gravitational pull of wherever, switch on, simple gravitational switch. On it goes again and starts doing things in that new environment. If we look at a probe or spaceship traveling a long distance from one solar system to another, then how could it get energy to do that? Well, firstly, it might actually not need much in the way of energy just to continue once it's moving, but it could perhaps soak up energy from comets.
The machine exploits the chemical energy locked away in the rock and ice.
I think it's quite possible and sensible for a probe, having travelled many, many miles once it arrives at another planet, to have its own little chemistry set, as it were, to test out what's in the environment, what's there, what's possible and what's not. Quite simply, within itself, a computer-based form, could then evolve through many generations, and out pops a life form which is suitable for that environment. I think machine